So this is some joint work between JBoss and Newcastle. So I'm the JBoss bit, and the Newcastle bit's sitting over here. And it's about how to do top K queries, because thus far I haven't been able to find any presentations on this. There's one, I think, on video analytics that hints at it in one slide. So I thought it was about time someone looked at this in a bit more depth. So what is top K? That's the first question. You all use top K queries every day. Google search is a great example of top K. You give it some keywords and it gives you back the most relevant documents. And time series is another one. So this is an old tool called Analog. Anyone old enough to remember Analog Web Analytics before Google Analytics took over the market? Just put in something retro there to make the point. Top K queries have been around for ages and ages, and this is really about how do we adapt them to work on Cassandra. So we're not too concerned about the scoring algorithm for this presentation. Things have a score. We don't really care how it's arrived at. It could be PageRank. It could be simply counting things that have occurred from a log file. And there's two different application domains for those. There's document search, where we're looking at words. How often does a word occur in this document? How relevant is it? Or log analytics, which is normally counting things over a time period. How often was a particular news article accessed on the site in a particular month or week? And those require a slightly different approach, as we'll see, because they have slightly different characteristics. So isn't this kind of straightforward? I mean, you give this to any junior developer and they go away and they write this database query, and it takes them about 10 minutes, and yeah, lunchtime. Presentation over. Bye-bye, everyone. Not that simple, unfortunately. If we look at what this is doing, we have a table here that has some kind of notion of an identifier for the entity, the document, and some kind of score that we've computed by some algorithm we don't really care about. And we're filtering it based on things that are relevant to our query. So I've done a search for, show me all the documents that have top K in them, and show me the most relevant ones. I want to order them by score. So that the ones with the highest score, the most relevant ones, get at the top of the heap, and I'm going to limit it by K, because I'm only wanting the first 100 or the first 10 or however many. Very straightforward stuff, except it's not, because potentially I search on multiple terms. I can search for top K in algorithm, for example, and that's going to narrow the search down a bit, but it's going to make the search more complex as well, because now I have to do a group by operation. And this is where the problems begin, because whereas the first query, that is valid both in traditional SQL databases and in Cassandra, this one isn't, because I don't have a group by primitive in Cassandra anymore. So I'm going to have to do some more work here. I'm going to have to come up with a way of implementing group by on top of the data structures I have in Cassandra in order for this to work. Well, it turns out you can do that fairly easily as well if you're willing to go out and collect a few pieces. We have a lot of data, but it's spread out, so we need some way of gathering it together, essentially, to do this group by. And we need to do that fairly efficiently. So if we take efficiency to mean developer time, one of the ways we can do this is we can implement one of these tools that will allow us to take SQL queries, and we'll compile them down to Hadoop MapReduce jobs, and we can run that over our Cassandra cluster. So if we take something like Impala or Sting or any of this family of tools, we're pretty much done. We can just take that SQL query we've already got, feed it to the tool, and it'll give us an answer. So that's efficient in terms of the developer time. It's not efficient at runtime. It's going to give us an answer, but it's not going to give us an answer fast. And that's a problem because we're interested in real-time top K. And what I mean by real-time for the purposes of this presentation is not the old computing science, hard real-time, missile control systems, nuclear reactors kind of thing. This is web page rendering real time. This is milliseconds, perhaps a handful of seconds if our audience is kind of tolerant, but once you're up into tens to hundreds of seconds, no good. I'm concerned for the purposes of this presentation mostly with performance of query time rather than the timeliness of the lag between an event occurring and it being available to query. That's an interesting field. I'm happy to talk about that at lunchtime if you come and see me, but I had to throw out certain things to make this presentation fit, and one of them was the ingest bit of the pipeline. So the basic idea, as usual in Cassandra, is pre-compute as much as possible. We're going to calculate the scores ahead of time using whatever expensive algorithm we have for that, and we're going to store them into Cassandra's just pre-computed values. And we're going to assemble these pre-computed fragments with a group by operation at query time. So there's a few ways you can do that. You could issue a single query for all the data to Cassandra and then loop over it in your application code and your client. We do it slightly differently. What we do is we select for each term, we issue a separate select. And the reason we do that is that some of those are going to return fairly quickly, which means we can get on with processing them straight away in the client while we're still waiting for the other ones. So it cuts out a bit of the latency that you get if you just issue a single big query and rely on the Cassandra coordinator node to pull all that data together from the various nodes where it's actually stored in the ring. It's inefficient because we're still having to pull in all the data for each of these terms. So how much data do we actually need out of this big set? Can we limit it so that we're moving less data across the network and we can move it more quickly? So I'm assuming you know a little bit about CQL3. I was told the audience of these things was highly technical, but I was told that by a marketing guy. So, data is stored keyed on the term or the time period, depending on your domain. If it's document search, you've got the notion of a term, a word in the document. If it's searching events in logs, you've typically bucketed it by time period, which could be a day or a month or whatever. So you can limit that by querying over the partition key in your SQL query. You just say where key in, this term, this time period. And Cassandra will limit the amount of data it's looking at, the number of rows it's pulling off disk and sending to you. But what we really want to do is limit on the next bit. We want to limit on score as well, because we have a long tail effect here. We have a lot of documents that do contain the term, but have very, very low scores. So they're never going to appear in the top K. There might be scores over a huge range, thousands, and it's only one end we're interested in. We don't want all the rest, because if we get all of it, we're going to have to move it across the network, and that takes time, serializing and deserializing. We're going to have to look at it in the client and decide whether we want it or not, which is going to take time for the comparisons. It's not terribly efficient. It's not going to get us down to real time because our data set is so vast. So at this point, we need a clever algorithm. We can't rely on Cassandra to do this for us because we're getting into application-specific algorithms here rather than the more general data algorithms that Cassandra gives us. So at this point, we go out and see what's already been done because, as I hinted at earlier, this is a fairly old problem. Smart people have already thought about this. So there are some algorithms out there that kind of more or less do what we want. The difficulty is these are fairly old. They're not Cassandra specific. They're actually, turns out, mostly for doing log analysis in content distribution networks. So if you think about a content distribution network, it's a bunch of servers that are spread around the globe. They're linked together by a fairly slow, fairly high latency network. If you're serving, let's say, video files of these, each of these is logging what it's doing, who it's serving those files to, how many times it's serving them. But to get a global picture of your traffic, to know which were the most popular files in a given period, you need information that's spread around all these machines. So you need some efficient way of getting back just the top K, the top 100 most popular files you've served off your CDN. So these algorithms have been designed for this kind of environment, which looks almost like Cassandra in that it's a bunch of distributed nodes, except the network between them is different. What we have is a slow, high latency network, whereas in Cassandra, you're typically in the same data center, so you might have much more bandwidth and it's much faster. So we want to take these existing solutions and we want to adapt them to this new environment because these algorithms are already tried and tested. We don't really want to cook up something ourselves because we're going to make mistakes and it's going to take us longer. But at the same time, we need to be aware that the algorithms were not designed for exactly what we're using them for. So we need to keep an eye on that aspect of the problem. So what does one of these algorithms look like? I'm not going to go into too much depth. This is the kind of non-technical version, or semi-technical version. If you want to understand the algorithms in more depth, come and talk to us after, but the simplified version is this. They fetch a little bit of the data and they sample it effectively. They look at the characteristics of it and decide how much more they need, and they go and fetch that next chunk, and potentially they repeat that until they've got enough to be satisfied that they can give an accurate answer for the top K items. The problem with this is you don't want to do too many cycles of that, because each of those is costing you time. Each of them is a network round trip, and the milliseconds are mounting up, and your client's sat there in front of their browser wondering why their page hasn't refreshed yet. It's not good. So what you want to do is limit the number of rounds of communication. And there's a trade-off between using a few rounds in which you retrieve a lot of data versus using more rounds in which you retrieve only a little bit of data in each one. And there's some kind of balance to be hit there, and that's essentially what the algorithm's are trying to achieve. So in terms of evaluating these algorithms, the key is to look for ones that have a fixed number of rounds of communication, because that allows us to have a predictable response time. There's an upper bound on how long it's going to take. In the algorithms that don't have this characteristic, with degenerate data that's exactly the wrong shape, you're going to get into a situation where it's taking a great many rounds of communication, and that's going to blow your time budget. The other characteristic we want to look for, generality, particularly with regard to the distribution of the data. Most data follows certain patterns, and that's great, but sometimes it doesn't. And if the algorithms are being tuned or designed only for certain characteristics, sooner or later you're going to find suddenly your production data doesn't meet that expectation and things are going to start going wrong. So you want a general purpose tool where you don't have to worry about that. Ideally, since I'm a middleware guy, I also want it to be flexible, because I want to put this out to a number of different clients, a number of different use cases, and have them all be able to use the same thing, but ideally tune it for their specific environment. So some kind of flexibility, some kind of tuning in the algorithm would be a very useful characteristic. So if we go back and do a literature search, go and Google top K algorithms and look at all the academic papers that have been published, what you find is that there are three that meet these characteristics, more or less. And given that the work is done a little while before they're published, we're looking at work here that's getting on for 10 years old. There's three algorithms here. There's two from universities in the States and one from Europe. And the key difference here is that the top two are exact algorithms. I'll give you a precise answer. CLIA is a little bit different in that CLIA uses metadata to allow it to approximate the answers. So you can say, give me the top K with a certain degree of accuracy. And you're trading off accuracy against speed, essentially. You get a quicker answer, but it might not be perfect. And for a lot of applications, that's fine. You don't really care if down at the bottom of your top K range, the 100th item is actually the 101st, and you're not seeing the real 100th one because it's been demoted into the wrong place. That's okay for many applications. So, having identified the right algorithms, you then sit down and implement them, and you run into certain problems. And one of them is these algorithms assume server-side code execution. They're designed to have a proprietary server sat on the nodes where the data resides that can execute code that is specific to the algorithm. And that's a problem because what we have is Cassandra, and what it'll execute is CQL3. And if I can't express the algorithm in terms of CQL3, I've got a bit of a problem. Turns out there are certain steps in these algorithms that you can only implement on top of Cassandra if you're willing to incur extra round trips and extra transit over the network. And what you have to do is pull back more data than you strictly need in order that you can perform calculations on it in client code, because you can do whatever you like in the client. You can execute this custom logic and then send back additional CQL3 queries to the node that essentially contain the results of those calculations. So the problem with this is that the performance comparisons in the literature are no longer valid because they're assuming certain characteristics of the environment that don't hold for us in Cassandra. So we can't trust the evaluation of the algorithms anymore. We can't say, oh, look, in the literature, this algorithm is the best one. It's far more performant than any others. Therefore, I'll implement that one. Turns out it doesn't quite work that way. So you have to implement all of them and see how they compare. So fortunately, the heavy lifting is being done for you. And here are some results. This is data transfer over the network. So in the context of the academic literature, the algorithms that have been published, data transfer is the key metric because they're working on a LAN. Data transfer is expensive and slow, so that's what they're optimizing for. So the first thing to notice is the dotted line horizontally across the top of the graph there is the naive version, and it's way big. A lot of data moving there. That's going to be too slow for us. Most of the other algorithms, the clever algorithms, are way down at the bottom here, much, much, much more efficient in terms of the data they're moving. And the one to watch is that slightly sloped line. That at first glance looks like it's the worst of the clever algorithms. It's transferring quite a lot of data compared to the other ones, particularly as K grows. That's actually a variation we developed specifically for Cassandra, and the reason why is that when you look at execution time rather than data transfer, suddenly that line is down at the bottom. It's suddenly the most efficient algorithm in terms of execution time. So because we're evaluating against a different metric, because we care primarily against execution time instead of data transfer, because we're on LAN, data transfer is comparatively cheap now, we made some changes to the algorithm that make it more efficient. Essentially what we're doing there is, in the base version of the algorithm, we would have performed an inquiry over a very large set of keys. So the Cassandra node would have been doing a lot of comparison to decide which items to send us, a lot of seeks to find those items. Instead, we bound the range and we transfer everything and we throw away the ones we don't want. And if it's dense enough, if we want to keep enough proportionally out of that range, it's cheaper to do that.
Stuff to read here in the back, is that milliseconds on the y-axis?
That is milliseconds, yes. Very much depends on your test data, right? Take it with a grain of salt. What you're interested in is the slope of the lines, really, rather than the absolute numbers, because your data is going to differ, your network's going to differ. So that's as a function of k. Most of those lines, the line is sort of low enough in gradient that you can probably afford to calculate more than you want. So if, for example, there's a high probability the user's going to look at the top 10 and then click next, you could, for example, go for the top 20 straight off and just cache the second page ready for them. So execution time against peer. What the heck is a peer is the obvious question here. A peer is a node you want to talk to, essentially. Remember that the data is grouped by term. That's the primary key that's giving you the distribution into the ring. So this is the number of nodes, the number of Cassandra nodes you need to communicate with in order to pull back the data. So in a text-based search, your number of peers is fairly low. It's the same as the number of words you're searching on. So if I search for top K algorithm presentation, 3 words. 3 peers. If I'm using time periods, it's a slightly different dynamic, because if I want to graph, say, a month worth of data, or on top K, what was the most popular article on my website during the month of May, for example, if my data is bucketed into days, I've got on the order of 30 days, depending on the month, right? So we want an algorithm that's going to scale fairly well with the number of peers, and most of these do. One final one, you don't want to use tput. So I said there were 3 candidate algorithms, and they mostly work fairly well. They're mostly in the same kind of ballpark here, at least as far as the gray bit goes. That's the base case. I said your data can have different shapes, and one of the cases where that happens is where one of the peers is responsible for the bulk of the score mass, the bulk of the data. It's proportionally more important than the others. And if that happens, tput doesn't work so well. The other ones, for that kind of data, they actually get more efficient. That's the little black bit at the bottom of the clear and hybrid threshold. tput doesn't get anywhere near as efficient. In fact, it's very inefficient compared to the others. So your mileage is going to vary. Test this with your own data, test it on your own hardware, because you're going to have different characteristics to what we've tested with. In particular, try not to use synthetic data if you can avoid it. Try it with actual real-world data if you have it. But in general, the recommendation boils down to, if you want an exact answer, use hybrid threshold. And when I come on to the Intravert bit of this talk next, you'll see for implementing hybrid threshold, Intravert is kind of optional. You can actually express hybrid threshold pretty efficiently just in terms of CQL3. CLE is an approximate algorithm, so if you're happy with approximate answers, it's more efficient than hybrid threshold. You'll get an approximate answer faster. The downside is it does require some metadata. And for the really efficient version of CLE, there's an extra step in the algorithm that makes it more efficient, but which can only be implemented using Intravert. There's no way to express it efficiently in CQL3. So you've got a trade-off here between the characteristics you want. If you want absolutely great performance and you're happy for it to be approximate, CLE's the way to go, but you're probably going to have to deploy Intravert. If you want hybrid threshold, Intravert's essentially performance optimization. Which brings us on to Intravert. So what the heck is Intravert? Intravert is essentially an enhancement to Cassandra. It's a way to add extra functionality to the server. So what they're doing is swapping out the main class that boots the node, and in the same JVM, in the same process, they're bringing up a server that's based on Vertex. Anyone use Vertex? Anyone heard of it? Yeah, a few. Okay. So Vertex is a bit like Node.js in that it's a kind of app container based on asynchronous design. except it's for the JVM, so it's polyglot. Any language that targets the JVM will run happily in Vertex. So using this, they've added certain functionality onto Cassandra. The first thing they've added is a new API that's based on RESTful design principles, uses form of JSON as the data, HTTP as the transport layer. If you've worked with certain other NoSQL databases, you'll recognize that kind of design. It's great if you've got a JavaScript client that you want to talk direct to your database without an app server tier in the middle. It's kind of been done before. It's not absolutely novel and unique to Intravert. There's another project called Virgil that did this a little while back. But for our purposes, it's really not that interesting. We already have a perfectly good transport for our purposes in the form of the native protocol to talk CQL3 to the server. We only need this extra transport where we want to express Intravert-specific operations. We can do multiple commands per call, which is great. We can save on some round trips by batching things up. But we can also chain operations. So instead of sending a batch that will essentially execute in parallel, we can say, execute this operation and create what a traditional database would call a temporary table or a cursor, some kind of notion of something you can refer to in another query. Say, take the operation here and execute this next operation, pass the result set from one to the next using a reference. So Intravert gives us server-side code execution in pretty much any language, theoretically. In practice, the API right now is Groovy. We can do things like filtering result sets. It's fairly trivial. We can send a CQL3 operation and a filter expressed in Groovy. We can ship them over together, and it'll filter the result set on the Intravert node and send us back just the results that meet the filter criteria. We can do triggers. This is not so important if you've already made the jump to Cassandra 2, because obviously it now has trigger support, as you saw in the keynote. It's great if you're still stuck on the older Cassandras and want some kind of write path trigger. But unlike trigger support, Intravert will also do read path work, not just write path work. So you can execute arbitrary logic at read time. Filters is just a specialist case of that. You can also effectively extend Intravert if you're willing to hack it a little bit, to add extra operations. So the basic operations it comes with are the ones you would expect from Cassandra, gets and puts, and a few new ones to chain result sets and do triggers. But you can also arbitrarily extend it with your own logic if you wish. And doing that in Intravert is a lot easier than the way you had to do it in the old days in Cassandra, which was to extend the Thrift API. So in summary, Intravert is giving you a trade-off between additional power to express your queries, additional power to do operations on the server, versus operational complexity. Because it's embedded inside the Cassandra node, it's not adding as much complexity to your operations people as running a completely separate server. I can't very well go to the ops guys and say, oh, I want to do this top K thing, so here's a new server process, and you're going to have to put this on all the nodes, and you're going to have to monitor and manage it, and it's going to have memory leaks, and yeah, nightmare. Instead, any tool they already use to monitor Cassandra will monitor Intravert, because it's the same thing, it's the same JVM. Does add some development complexity. The API is not the same on the client and server anymore, so shipping code between the two does involve rewriting things a little bit. Also, obviously, it's more complex to deploy unit tests and things like that. Worthwhile trade-off for cases where you've tried it in CQL3 and you know you've got a performance problem. Good to bring this in, bring in Intravert as a tool to solve those few cases where your client is getting overly slow or overly complex because of the limitations of CQL3. One of the drawbacks, at least for our use case in the client, is that the Intravert client's not really got a great awareness of Cassandra's ring topology. So I mentioned earlier, one of the things we do is that instead of sending a single query to a random Cassandra node, which acts as the coordinator, and expecting it to farm that out to the data nodes, we send a bunch of queries in parallel to each of the nodes that owns the data, and that cuts an extra network hop out of the cycle for us. That's tricky to do with Intravert because it's not designed to be deployed that way. The way you normally deploy Intravert is you deploy a few servers as Intravert servers And because they're also part of the ring, they're communicating for you. So they're both the coordinator in Cassandra terms and the app server, if you like. We instead deploy so that every Cassandra node is also an Intravert node, and we want to talk direct from the Intravert client to whichever one we know owns the data. So that adds a bit of complexity to the client code. Compare that to the Java driver, say, for SQL native protocol, which just you plug in a new policy for load balancing that says, use your knowledge of the ring topology to dispatch this directly, and it does that for you. So let's return to these clever algorithms. With Intravert, we can now do server-side execution. So we can now have an execution model that more closely maps to what the designers of these algorithms intended. We can implement this code much more cleanly compared to the description of the algorithm that's been provided to us. We don't have to put in new round trips just to cope with the limitations of the query language that Cassandra gives us anymore. Trade-off for that is we have added some development complexity and some operational complexity, but it's a nice middle ground between the complexity that we would get, the much larger complexity we would get if we wanted to deploy a completely custom server. We can reuse a lot of our existing Cassandra tools to do this, whereas we couldn't if we had to write a completely custom server. Okay, what have we got next? Pre-aggregation, right. So I showed graphs of the performance scaling as a function of the number of peers. One of the things you can obviously try and do is reduce the number of peers you've got, and that means using denormalization to pre-calculate the aggregates. So it's hard to do for text search because it's very difficult to predict which terms are going to be queried together. There's a handful of cases where you can do it. People's names, for example. If someone searches for Justin and they search for a second word, odds are it's going to be Bieber, sadly. So there are certain combinations you can pre-calculate, but by and large you can't tell what's going to be queried together. The state space just gets far too big if you're trying to do all possible combinations. Time periods is different. Time periods, you're almost always going to query contiguous time periods. So there might be days that are next to each other to form a week, or weeks that are next to each other to form a month. So pre-calculate these roll-ups, because that's going to reduce the number of buckets, the number of peers you need to query. This is where the choice of algorithms becomes important, because now you might have a query that spans over a big bucket, like a month, plus a number of smaller buckets, like days, to bring you up to the exact time period you want. And in that case, one of the buckets has a much greater importance, much greater weighting than the others. So that's why you want to avoid the algorithm that doesn't scale well when your data has that shape. Okay, really, really clever algorithms. If that wasn't enough to make your head explode, we can get into some more complex models. I've been using the term peer to mean a Cassandra node, a place where data resides there, and said the number of peers you need to talk to is the same as the number of query terms you have, roughly. This is not quite the case, because the hashing might mean that certain bits of data are actually co-located. Certain logical peers in the computation might have a hash such that they're actually physically located on the same Cassandra node. And in that case, what you'd like to be able to do is talk to that node and say, hey, I know you own the data for this peer, and what I'd like you to do is jam them together and send me back the pre-aggregated data. Do a local group by over just those terms, send me the results, and then I'll do another group by over all the joined up results I've got from the nodes. So you're building a two-level hierarchy. You're doing group by in the client, but you also, where you can, doing group by on the local data-owning nodes. And that saves you a lot of extra transfer in cases where you have a very high number of peers and therefore a high probability that some of them are going to map to the same number of Cassandra nodes. It's all about the ratio between the number of peers and the number of actual nodes involved. Again, your mileage is going to vary depending on how many nodes you have in the ring and how many peers you're querying over. Some very interesting later work on budget constraint, top K. So this is where you can tolerate approximate answers and you have some kind of time budget. I want an answer within 30 milliseconds, within 300 milliseconds. Whatever my time budget is, just give me the best results you can in that time period. It doesn't matter if they're not perfect, I have to have them quickly. So there are certain algorithms that are aware of budgets You can express that budget in terms of a number of constrained resources, but most likely time and potentially number of I/O operations. So one of the things we want to look at in future work is how can we design an algorithm, how can we implement an algorithm that is aware of how much work Cassandra is having to do to implement certain primitive operations. We also want to look at some notion of fault tolerance. There are cases where nodes are down. Ideally, you've got enough fault tolerance just through replication to deal with that, but there are cases where you haven't, or where you haven't noticed the failover, and by the time you do, it's too late to reissue the query. And in those cases, you'd like to be able to give back an approximate answer and say, hey, I've done the best I can given the data I was able to obtain and given the time I had available, and I think this answer is probably accurate to within whatever. And then the client can choose whether to use that or not. It can say, that approximation isn't good enough, I'm going to have to introduce some extra time here while I go and try it again. Or it can say, oh, I'm out of time, I'll just have to go with the best answer I have. So those are very advanced bits we haven't got around to implementing yet, but show you that this is really just the tip of the iceberg in terms of tuning this for certain use cases. Phew. Okay, made it to the end in time. Time for questions, if you have any. Have I made your heads explode? No, you're still with me. You really are a technical audience. Great.
Are you opening any of the source?
We hope so, yes. It's at sort of research prototype stage right now, so don't expect to be able to put it straight into production, but yeah, it's a case of cleaning it up a little bit, you know, making sure the tutorial works basically and slinging it out there, so yeah, expect it soon.
You mentioned the relative impact of the Intravert and Cassandra portions of queries.
Right, so inside the client, we time each operation, and some of those are SQL operations and some of them are Intravert operations, but we can break down how much data each is transferring and how long it's taking. So we know roughly what the impact is. There's no way to do a real like-for-like comparison in some of the algorithms. We're not really comparing, say, native transport versus introvert. The native transport is more efficient and we're using it wherever we can. We're only using introvert for the steps where we don't have any alternative, where we would otherwise have to do something hugely inefficient like pulling a lot of data to the client, distilling it, and then sending back another query that just has some parameter calculated from that data. So introvert in those cases is always more efficient. All we're really interested in is, the absolute amount of time it's taking and can we tune it in any way. The more interesting comparison for me is going to be as and when the trend we're seeing to add server-side execution capability starts to come in. We've already got that with triggers for the write path. There's hints that it's coming for the read path as well in terms of the ability to do certain operations, but potentially just aggregates to start with, but eventually arbitrary code execution in the read path. Stored procedures, essentially, right? Comparing that to introvert would be really interesting. And eventually, hopefully, taking introvert out the picture, and as all the capability we need comes into Cassandra itself, we can phase out introvert. Introvert is kind of a stepping stone because Cassandra doesn't have this functionality yet. Another interesting benchmark I'd like to do, and haven't had time for yet, is to port this to HBase, because HBase has co-processors. It already has read and write side arbitrary code execution on the server. So benchmarking against HBase would be a really interesting one. Any more questions? Yeah.
Intravert be a solution to efficiently sampling a number of rows, let's say, for example, from a very large column family?
Sampling, you want a random every 10th one or whatever.
Let's say you want 2,000
Right.
out of 10 million random.
Yeah, so there's a couple of problems with that. You have to know how many there are if you're going to stream it, right? So you have to pre-calculate that. But assuming you've got that information, yes, because you're writing effectively a filter.
Yes.
Yeah, it's very efficient for that. Okay, I think that's it. I'm going to be hanging around here a little while longer. But if you want to go and get lunch, that's great. Thank you very much for coming.